multi-neutron clusters and systems followed by quasi-free scattering reactions, mainly focusing on tetraneutron and oxygen-28. Okay. So let us start. So we'd like to discuss multi-neutron systems or pure neutron nuclei. This means that it's a Z equals 0 element, or we can call neutron droplets. So the question I'd like to raise here, if there are any nuclei made only of neutrons. So here you can see here from dineutron to neutron star actually. So dineutron to neutron system is not bound and no resonance. Only we know that scattering length, and maybe we can set the lifetime less than 10 to the minus 20 second. And tetraneutron is a kind of now a hot topic. Lifetime bound or resonance, those are questions. Okay, in between, of course, we have 3 neutron. 3 neutron was measured last year, I think, and maybe this will be discussed in the workshop by Miki-san, I think. And hexaneutron, the next candidate, but this was never measured. But maybe 6 neutron system may be more stable because of the P3 half closed, semi-closed shell. And of course, we are interested in some number of neutrons which may be more stable than the others. Then maybe we have new magic numbers. And then, of course, at the end, we have this neutron star. Of course, neutron star is not pure neutrons, we know, but lifetime is infinity. But there are many questions, as we heard from Ingo's lecture. Neutron star radius or maximum mass compositions, not yet established, I would say. Okay, so our interests are mainly the few body systems and these tetraneutron, hexaneutrons. Those are important benchmarks to understand 3 neutron forces, 4 neutron interactions, and neutron correlations, multi-neutron correlations, and magic numbers, and so on and so forth. And then this can be a test benchmark for the ab initio calculations, or even lattice QCD. And then this kind of information can be used to establish the equation state of neutron matter or neutron star. And we have also some kind of universal features as a fermionic systems, many body systems. Okay, this was already discussed. The question is what happens when neutron drops are introduced in a nucleus. So this was about dineutron, and this was about tetraneutron. So not only the pure neutron systems, we are also interested in tetraneutron inside a nucleus. If correlation is stronger, if 4 neutrons are inside nucleus. So this was also discussed already. So this is about dineutrons, and yes, this is about 4 neutrons, helium-8, 490. Now I corrected for this core, and then oxygen-28, which we discussed here also. Okay. And well, I found actually a very interesting paper about neutron drops in an external field. This is ab initio theory by this group. And they use quantum Monte Carlo QMC for using AVA prime interactions, and also no-core full configuration, no-core shell model using JISP16 interactions. So what they did is that they calculated the energy of or mass of neutron droplets in an external field. External field is prepared by the harmonic oscillator. Okay, This is their result. So depending on the harmonic oscillator depth, this is 10 MeV case, this is 20 MeV case. And this is according to the neutron numbers. They normalized the mass with some factors. But anyway, what they say is that interesting feature. So this is a free neutron. So basically, because of this potential, these neutrons are bound. Okay, but they found that 3 neutron is least bound. Okay, so it's most unstable. But then you find some interesting features at 8, 20, and somehow 32. So this means that 32 could be a magic number. But to get this magic number, they needed to include 3 nuclear forces. So this is already telling us that this kind of study for neutron droplets are interesting to get information about nuclear forces. I mean, 3 nuclear forces, for instance. Okay, so I just would like to review the recent experiments on tetraneutron. So tetraneutron experiment was kind of triggered by this measurement by Miguel Marquez in 2002 using barium-14 beam on carbon target. What they measured is a barium-10 plus 4 neutrons. Okay, so this is the spectrum. So this is the neutron. Okay, so this is actually the recoil proton energy versus the incoming neutrons. So what they found is that recoil proton has rather large energies in these 6 events. I think 1, 2, 3, 6 events, and in here they show the particle identification spectrum. So you see here is a particle identification peak for barium-10. This is, I think, barium-12. So if these 6 events are kind of in coincidence with barium-10, and this excess, they claim that this is due to this resonance or bound tetraneutron state because of the because of this high tetraneutron. Maybe the recoil proton has larger energies like this. So this is a kind of trigger for this tetraneutron. But finally, the conclusion was not so, clear, I think, because, sorry. Okay. Anyway, so the next measurement was, this was also introduced by, I think, who was that? Yeah, but anyway, I explain. Helium-4, there was a measurement, helium-4, helium-8, barium-8, tetraneutron. So this is a double charge exchange, it's called, because helium-8, barium-8 exchange 2 charges, 2 electric charges, right? So helium-8 impinges on helium-4 target, okay? Then 2 protons are removed from helium-4 into barium-8, and 2 neutrons are removed from helium-8 to 4 neutron system, like this. And the barium-8 is, we know that it is very unbound. It decays into helium-4 to helium-4. So what they measured is this helium-8 momentum and also helium-4 momentum. So then extract the mass of this 4 neutron system as a like this. Okay, so before going into that, I should explain this thing. So there is a very interesting trick behind, namely to produce a tetraneutron system at rest, right? So what they did is like this. So from helium-8 to barium-8, the Q value is 26.37 MeV. This means that it emits some energies, right? But this energy is compensated by the difference of tetraneutron relative to helium-4. so that the energy was kind of transferred like this. So then the momentum transfer becomes very small. So this means that you can make helium 4-neutron system at rest, basically. So this is very important because if this condition was not met, this means that you have a higher momentum transfer that breaks easily this tetraneutron resonance or whatever, the 4-neutron system. So this was the idea by Shimura-san, the second author of this paper. Okay, and then what they observed is this missing mass spectrum. So found a peak just above the threshold of 4 neutrons. They obtained the energy 0.83 MeV with these errors, statistical errors and systematic errors, and the upper limit of the width 2.6 MeV. The event number was just 4, so 4 events. With 4 events, but a rather isolated peak was found. Okay, and there's another one which was published in 2022. So this was by Festerman et al. Okay, so this measurement actually uses not radioactive beam but stable beam, lithium-7 on lithium-7. And the experiment was done at tandem accelerator at Garching near Munich. This facility was, I think, closed after this experiment. But what they measured is lithium-7 on lithium-7, 6.5 MeV per nucleon, and then produce carbon-10. So they measured carbon-10, and the counterpart should be 4-neutron system, right? So this is a mass kind of transfer reaction experiment. And what they found is this kind of spectrum here. So this is energy of carbon-10, this one, but okay, so this peak, big peak, is due to the oxygen-16, lithium-7, carbon-10. So this, because the target, lithium-7 has a contaminants of oxygen isotope, so that's why this peak appears. But they claim that this another peak is due to lithium-7 going to carbon-10 tetraneutron. Okay, and okay, and then they found that, okay, so okay, I think I can see it. Okay, so this corresponds to the excitation energy 2.93 plus or minus 0.16 MeV, and the width is less than 240 keV. So if the carbon-10 is at the ground state, the energy is actually 2.93 MeV. But what they claimed is that because of the width is so narrow, so this shouldn't be the resonance state, but bound state. So they claim actually that the carbon-10 is not at the ground state, but the excited state. So the excitation energy is kind of covered by this carbon-10. So the tetraneutron becomes the lower energies, becoming bound state at 420 keV bound. That was their actually claim. Okay, if that's the case, that's very exotic, of course. And if that's the case, the lifetime becomes like 450 seconds because this tetraneutron can decay only by beta decay, and also this can happen only first forbidden transition, so that the lifetime becomes like this. So if this is the case, maybe we have lots of tetraneutrons floating in the universe, maybe. If some explosion occurs, maybe 4 neutrons there for at least like some minutes, 10 minutes, yeah, some couple minutes, right? Yeah, 8 minutes or something. Okay, so this is another experiment. And finally, this is a famous one, done at PP alpha reaction, quasar-free scattering in inverse kinematics, actually published Nature with the first author, Dewar. Yes. So in this experiment, helium-8 impinged on proton target, like this, and the alpha particles are just knocked out. And so then p proton is going like this, and the remaining particles are 4 neutrons. Also, there was a trick here. We used backward scattering, namely that we actually, in normal kinematics, you can understand better. So proton is hitting these alpha particles, and a proton should be, coming back to the beam direction. So 180 degrees, nearly 180 degrees. I think we maybe selected like 160 degrees or so. But anyway, backward scattering is used. So this is done because that by doing that, we are sure that 4 neutrons are intact. We just, knocked out alphas only, right? So the 4 neutrons are kind of intact, like this. And this can be shown actually here. So, in the normal, even for the inverse kinematics, the velocity is very different. So you see that this is momentum per nucleon. So this corresponds to the velocity, basically, velocity distribution for coming helium-8, and this is proton, and helium-4. So you see that, in this case, proton is kind of accelerated. So this corresponds to the acceleration of protons, while alpha particles here is kind of decelerated, because, so so this is, now I discuss in the inverse kinematics, and then helium-8 is here. So indeed, we actually selected this kind of backward scattering one. So with that, actually, using large momentum transfer, we can minimize finite state interaction, right? If this is not like that, maybe alpha particles, the protons are hitting this tetraneutron, and then this will disturb the production of tetraneutron system. Okay. So this is the experimental setup. We use the summary setup, as we explained already. So we used helium-6 beam, helium-8 beam, both used at 156 MeV per nucleon. And then we have this system here like this. We have a liquid hydrogen target, about 5 centimeter. We use a so-called MINOS system. And then silicon trackers here. So we measured the helium-4, but it is slow, so it's actually bent more than the protons. You know that usually, if the velocity is the same, helium-4, proton is bent more, right? Because of the charge to mass ratio is smaller for proton, right? But it's opposite. This actually shows that proton is very fast and helium-4 is slower. So that is happening like this. And the neutrons are going straight here to the neutron detectors. But in this experiment, actually, we didn't measure neutrons. We just concentrate on the measurement of helium-4 and protons because we used missing mass spectrum. So indeed, this spectrum was extracted by just measuring incoming helium-8 and outgoing protons and helium-4. To extract the missing mass of 4 neutron system, and then the peak appears, narrow peak appears here, and also some phase space decay occurs here. So we identify this as a candidate tetraneutron at 2.37 MeV with the width of 1.75 MeV. So and this is the summary of what we observed from different experiments. So this is 4 neutron energies. This is width. So this is a 0. So this is a threshold energy. And this is, what is this? This is a calculation, quantum Monte Carlo calculations. So the experimental value for this Dua et al. Is here. And Chirac, this is the double charge exchange reaction. Kisamori et al. Is here. And Munich group is here. Actually, they claim it's bound. Yeah, so like this. And the other calculations are also shown. And of course, as we heard from Hiyama-san, many theoreticians still doubt about this, I think. Yes, so maybe, but before going into this claim, but maybe we can just show you this consistency between helium-8 PP alpha and helium-4, helium-8, barium-8, these double charge exchange reactions. So you see that this is the threshold, and the peak is here. So basically, these two experiments are consistent with each other. Okay, and even for this phase space part, is almost the same. So the question I'd like to raise here is why this is so identical. I mean, I think no theoreticians can answer this so far, I think. Okay, so this was also discussed by Hiyama-san, I think. So why is it moving, by the way? Okay. So this is earthquake, because it's vibrating. I don't know why, but anyway, Lazauskas, Hiyama-san, Carbonell showed this spectrum of 4 neutron, and they say that the peak can be explained by the dineutron emission from the neutron density distribution just after 4 neutron removal from helium-8. So this means that it's reflecting the dineutron correlation inside helium-8. So this was due to the initial state, if I'm correct, right? Yeah. So that's, and then with that they can extract this. And the other claim is like a peak just above the 4 neutron threshold can appear without resonance, Del Tuba et al., for instance. And they said that maybe the peak should have a 1 over square root energy shape. And by the energy resolution, maybe this can be also like this, and so on and so forth. So this means that we need to measure more this tetraneutron, where energy spectrum with better energy resolution is required. And since, as I said, in this measurement, we extracted this peak using the missing mass. And we know that 4 neutron coincidence measurement using invariant mass gives us much better resolution. So that this project is now going on, actually. In several projects, well, at least 2 projects are going. And with that, we can determine also 4 neutron decay scheme. Like, for instance, if the 4 neutron decays, like 2 neutrons, probably we can look at such decay modes also. Okay, so I think, okay, so 25 minutes. Okay, the next? Yeah. Yeah, okay, yes. Thank you very much. So now I'd like to move on to oxygen 28. Before that, I'll take water. Now oxygen 28. Okay, so oxygen 28 is located here. Okay. Yes, here. And also oxygen 27. This was also published in Nature. Okay. Yes. Okay, why oxygen 28 we would like to see? Because this is candidate doubly magic nucleus, in a sense, by Meyer-Jensen's view. Namely that we know that canonical magic numbers, 2, 8, 20, 28, 50, 82, and 126, right? But, and if you look at the magic numbers like this, okay, you can see doubly magic number, doubly magic nuclei like this. But actually, we don't have many doubly magic nuclei. For instance, for stable doubly magic nuclei, only 5. Helium 4, oxygen 16, calcium 40, 48, and lead 208. That's all, right? Of course, doubly magicity are established for these 5 species. And if you extend into neutron-rich or proton-rich regions, exotic nuclear regions, even so, we can find probably only 7 more, as shown here: helium 10, oxygen 28, nickel 48, 78, and tin 100, tin 132. And before our experiment, except for oxygen 28, other nuclei were already observed. Actually, here you see nickel 78 was observed in 1995, I think in GSI, and almost at the same time in Ganil. Same here for tin 100. I think tin 100 was also kind of competition between French and German, like Ganil and GSI almost at the same time they observed. Nickel 48, 48 was observed in Ganil in 2000, something like this. Yeah. But oxygen 28 was not measured before. And I think we still discuss this magicity. Magicity was, I would say, established for nickel 78, tin 132, we are sure. But others still, we have some discussions about the doubly magicity. So first, we would like to observe oxygen 28. Second, we would like to see if this is really doubly magic or not. Okay. Let's see. So if you look at this region of nuclear chart, so this is Z equal 8, this is N equal 20, okay? So this is really the crossing point, oxygen 28, if we believe normal shell ordering, right? But if we believe no shell ordering, then we shouldn't have any halos in these regions, because this region is basically F7 half neutrons are there, right? But now we know that because of the island inversion, N equal 20 magicity is lost, and there is a mixture between D3 half orbital, this is here, F7 half, P3 half, everything is mixed here. So this means that we have P-wave component. P-wave means L equals to 1, so the condition of halo is met. So indeed, we have observed several halo states in fluorine 29, neon 29, neon 31, and magnesium 37, like this. Okay. So, so the question is, oxygen 28 is magic or not? Just briefly, maybe you are all theoreticians, so you know island inversion? Yes? Maybe I just would like to remark a little bit. Okay, so island inversion was first proposed by these people, I think, in 1990s. Warburton, Becker, Brown, theoretical paper. They found that further evidence for the presence of an anomaly in binding energies for the island inversion centered at Z equal 11. Sodium and N equal 21 here is obtained by comparison shell model calculation to experiment. So this means that actually compared to the shell model with a normal shell model without assuming any mixture of D3 half and F7 half, then these 9 nuclei have some abnormal behavior about the mass. Okay, so this is now understood that, well, actually they also found that they say that it is found that for Z equal 10 to 12, neon to magnesium, and neutron number 20 to 22, and possibly even larger neutron numbers, those nuclei, for those nuclei, the lowest 2 h bar omega state is more bound than the 0 h bar omega ground state. This means that, okay, so this is the 0 h bar omega configuration, the normal configuration, okay, right? But the 2h bar omega means that two neutrons are excited to this FP shell, like this. Normally, we know that this is excited state, right? So the energy is lowest here. But for some reasons, this becomes a ground state, namely the mass is smaller than this one. So this is called island inversion, and this happens because that there is some correlations energies. So by exciting two particles here, then this configuration gains some energies, and this energy gains obtained by actually deformation. Okay, by mixing these, it is largely deformed, so that it gains some energies. So that is this mechanism of this island inversion. Okay, so this means that not n equal 20 majesty is anyway no longer existing here. Okay. And okay, so this is like this. So the because of the correlation energies, what is this? Yes. So this excitation energy is kind of compensated by the correlation energies. And of course, there's another point, weakly bound effect. Okay, I don't discuss this, but weakly bound effect actually causes so-called Jantella effect. So this will induce some deformation. That is that is also discussed in this mechanism. Okay, so now I come here. So this is called the island inversion, where deformation is developed. But now even fluorine isotopes have been found in the island inversion. For instance, fluorine 28 was measured. This is resonance state, was measured by Adric, Revo et al. This was also a Samrime experiment at the Riken experiment. And the ground state was found, P-wave dominant. And fluorine 29 was measured by these people. Also, this is Riken experiment. And P-wave 2 neutron halo was observed, was found by this. And also the excited configuration, actually, they found the excitation energy of the first excited state is consistent with n equal 20 majesty lost. So, yeah. So this is found. So this is now, island inversion is now here. So now, really the question is here. How about oxygen isotopes? About oxygen isotopes, there's another point, namely it's called oxygen anomaly. So you see here the drip line shape is very funny, because drip line is usually gradually changing like this, but suddenly it has some vacancy here. So namely, for instance, if you look at the oxygen isotope ends at oxygen 24, neutron number 16. But if you add only one proton, then the neutron drip line extends up to fluorine 31, neutron number 22. Okay, 6 neutrons difference. Okay, and this is not easily understood theoretically, because many theories actually predicted oxygen 28 is bound, maybe some 10 years ago or something. Okay. But this group, these recent calculations show that this unbound of oxygen 28, 5 to 28 can be explained by introducing 3 nucleon force, okay, as discussed in these people. Okay, about oxygen 28, we also interested in if there is some 4 neutron correlation, because for oxygen 24, well, sorry, I didn't mention that, but okay, so there's another thing about oxygen, because oxygen 24 seems to be doubly magic, namely the n equals 16, this is neutron number 16, is found magic in oxygen 24. If you measure the, for instance, the first excited state of oxygen 24, it's rather high, 3 MeV, I think 4 MeV or something. So This is doubly magic. So in that sense, oxygen 28 has an oxygen 24 core, very tight core, and surrounded by 4 neutrons. So 4 neutrons may be correlated in oxygen 28. So what was known of oxygen isotopes beyond the neutron drip line before our experiment, so namely oxygen 25, 26? For oxygen 25, there were 3 measurements, all consistently show that the ground state of oxygen 25 is at 750 keV, above the threshold, and the width is about 90 keV. Okay, this is very simple. And oxygen 26, it was a little bit tricky, but finally we could determine the spectrum like this. Interestingly, the ground state is only 18 keV above the threshold. So very tiny difference. I mean, tiny, subtle, only subtle difference. Maybe this could be bound, right? Only 18 keV means that if there's something wrong, maybe this could be a bound state. Anyway, this is unbound, but only 18 keV. And then we also observed the first excited state at 1.28 MeV. So if you summarize these observations, so oxygen 24 is here, oxygen 25 is 750 keV above threshold, oxygen 26 is only 18 keV above the threshold, so it cannot decay into oxygen 25, only decay into oxygen 24, and first excited state is here. Okay, this was the situation. This is the situation in a sense. Fine. So the experiment. So okay, coming back to oxygen 27, 28 measurement, we use fluorine 29 beam. Okay. Okay, impinged on. Okay, maybe I'm not so sure. Sorry. I think I skipped one slide, or maybe I didn't include it. Okay, sorry. Okay, so the experiment, maybe I just use Blackboard, maybe. Okay. Yes. So as you see, we use the fluorine 29. So fluorine 29. Impinged on the proton target. So this is liquid hydrogen in reality. Yeah. And then we just remove one proton from here. So this proton is knocked out like this. Okay. Like this, okay? And then if you remove one proton from fluorine 29, the remaining particle should be oxygen 28. Like this, okay? And then this oxygen 28 is unbound, so it decays into oxygen 24 and 4 neutrons. Okay? So now what we measured is actually all these particles, all 5 particles are measured. Oxygen 24 was bent by the dipole magnet and tracked by these drift chambers, and we measured those time flight, delta E. So this is oxygen 24. And the remaining 4 neutrons are just going through the gap of the magnet and reached these neutron detector walls. Okay. So there were some tricks here. One is the target. We used the MINOS target, it's called. So MINOS target is a liquid hydrogen target, but 15 centimeters, so this thick, okay? Maybe this thick, okay? This is very thick, actually. But the trick is that it is surrounded by the time projection chamber. Time projection chamber can measure the recoil proton here. Recoil proton can be measured. This recoil proton can be measured. So if you measure this proton recoil, then you know where the reaction point was, right? here, maybe this is proton. So you know the reaction point is. Then, even if it is a thick target, one can calculate the energy loss of the beam and also the energy loss of the this outgoing particles, because we know the position here. So that helps us to improve the energy resolution. So even if we use this kind of thick target, we don't lose energy resolution. Well, this was an idea by Alexandre Aubatelli when he was in Saclay. So this was developed in Saclay, France. So the French team introduced this. And then for neutron detectors, okay, so we introduced Neuland neutron detectors in addition to our nebula detectors. So, so this was from GSI, actually. So German team wrote us this Neuland detectors. So this enhanced neutron detection efficiency very much, 50% efficiency for 1 neutron, and 4 neutron is like 0.1%. Okay, so this is actually a large collaboration, international collaboration, because they know that only RIKEN can measure oxygen 28. Okay, so now coming to the energy spectrum for oxygen 27, 28. So oxygen 27 means that we have oxygen 24 plus 3 neutron in coincidence. So now you know that the 2 neutron is already very difficult. Now we started to measure 3 neutron, 4 neutrons in coincidence. So this is the first, I think, successful experiment for measuring 3 neutron and 4 neutrons in coincidence. Anyway, for oxygen 27, we identify this small peak as the ground state of oxygen 27. And the width is less than 180 kV. And then maybe you may wonder, what is this peak? We identify this peak is the decay of oxygen 28. So this fitting actually comes from the assumption that if this is coming from oxygen 28 shown here. So maybe I should explain this. Oxygen 28 spectrum is like this. Oxygen 24 plus 4 neutrons. Maybe I should explain also this one. Okay, so if you measure this, this means that this is fluorine 29, P2P reaction it's called, right? So if you remove one proton only, but if you remove proton, 2 PM, 2 proton and 1 neutron, then this becomes oxygen 27. So oxygen 27 and oxygen 28 are produced in the same measurement. You know, yeah, sometimes oxygen 27 is produced like this, but sometimes oxygen 28 is produced. I think the cross-section is larger of oxygen 28, maybe. So that's why we have larger peak here. But of course, if you would like to measure 4 neutrons, reduce efficiency so that the counts are smaller here, okay, like this. But anyway, we identify this peak at 0.46 MeV, and the width is less than 0.7 MeV.
I'm not understanding. You are looking to oxygen 24 plus 3 neutrons. How
Right.
do you see oxygen 28?
Yeah, so this is like, okay, so this is like this. So okay, so if you can identify everything, okay, we can plot here like this. But the efficiency for 4 neutron is less than 3 neutron efficiency. So this means that sometimes we cannot measure this. We cannot measure this. Yeah, kind of contamination due to the 4 neutron channel, but if we cannot measure this, then it is plotted here, right? Interesting, no? Yeah, in a sense, inclusive in terms of 4 neutron measurement. Yes, yes, yeah. And well, there's another trick which was important. actually, if we actually plotted this oxygen 24 plus 3 neutron here, we found that actually the peak oxygen 27 was very tiny. But when we, so what Kondo-san did is that we just sorted out the neutron, 3 neutrons like this. So the relative energy between N1 and oxygen 24, N2 and oxygen 24, N3 and oxygen 24, you can extract event by event, right? And then we just sort it out, like the energy of this N1 should be smaller than N2 and N3 like this, okay? And then we selected E0. Okay, so then also we sorted out also three body energies, like 2 neutron plus oxygen 24, like this, and then also like this and like this. Okay, so if you select the lowest 3 neutron energies, less than 0.08 MeV, 80 keV. Okay, maybe it's a little bit detailed, but this just corresponds to the selection of oxygen 26 ground state. Okay, I mentioned that oxygen 26 ground state has only 18 keV. So if you select oxygen 26 in the decay here, so we just identify oxygen 26 here, then this spectrum becomes like this. So this peak becomes more pronounced. So this means that this peak actually decays through oxygen 26 ground state. So once we select this oxygen 26 ground state, then this peak is pronounced. Okay, so this is interesting, and that tells us that oxygen 27 decays actually through this ground state. Actually, same is true for oxygen 28. Okay, so yes.
This is very subtle.
Yeah.
Let's go back to
Yes.
the transparency.
Yes. Just a moment. Yeah, sorry. Oh my God. I pushed the wrong button. Where was it? Here. Yes. Yes.
Okay, so now you say E03, that is that neutron, is far. So, but this is part only of your kinematical window. It's going fast. E03.
E03. Ah, yes.
Then you say that your oxygen, you characterize with E02, E01,
E01.
smaller than E03.
Yes.
Characterize oxygen 26. Is that
Yes.
why?
Yeah, so what I said is that the, okay, so energy is kind of shared by these 3 neutrons, right?
Yeah.
Okay, so shared by like this, and then we just select the lowest 2 neutrons, lowest 2 neutrons. Then this means that we kind of select lowest one, and if we select the lowest one less than 80 keV, meaning that should be oxygen 26 ground state, then so this can be identified as an oxygen 26 ground state. Okay.
Big peak or the small peak? That is the
Small peak. Yes, this small peak I'm talking about. This big peak is due to oxygen 28, as I mentioned.
and the small peak.
Is oxygen 27.
But why you wrote 27?
Because this is 3 neutron plus oxygen 24. This is the same figure as in this one.
Or is the decay channel? This is why you are indicated by oxygen 27 in the other. It's just the decay channel. Yeah, that you indicate by
This one?
oxygen 27 in the figure. You see? You say
Yes. Yes,
but
oxygen
this
20.
is indeed is oxygen 26 plus 1 neutron.
Yes, yes, that's what I mean. Yes.
Not in the oxygen 27 state, but just
Okay. So yeah, you can say that. But okay. So what I'd like to say is oxygen 27. Of course. So oxygen 27 is like oxygen 24 plus neutron, 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 right? But what we found is oxygen 27 is decaying through oxygen 26. So like the oxygen 26. So this is oxygen 27.
Is the interpret, okay.
Yeah, so our interpretation is, but anyway, we have a peak like this. So this means that this is a resonance as a oxygen 27 anyway.
So oxygen 27 is a resonance built by a resonance of oxygen 26, or is bound oxygen?
Okay, it's difficult to say because that what I'm saying is that oxygen 27 is a resonance like this narrow state, but it decays through oxygen 26 ground state. So, but this is because that okay. I think this is yes. Yes, there is of course, there is a possibility that it can decay through here, oxygen 25, but this is not occurring, but this is the case. So, and there's and also of course there is a possibility that oxygen 27 decays directly to oxygen 24, democratic decay it's called. But for some reasons it decays through here, and this is not due to yeah, there is some theory. Looks like this is kind of favored due to some, I think, the penetrability discussion. So rather than decaying into here, it decays through oxygen 26, which is favored because of penetrability. Yeah, you know that how neutrons penetrate from oxygen 27, right? Yeah.
Oxygen 26 is bound.
Oxygen 26 is unbound, also unbound. That's why we needed to measure 3 neutrons, right? Oxygen 26 emits 2 neutrons also, okay? So these 2 neutrons are very low energies relative to oxygen 24.
It's not a resonance.
It's a resonance.
It's a resonance.
Yes, it's a resonance.
So it's a resonance on the top of another resonance.
Yes, so this is interesting, right? So this is the oxygen 26 resonance. This state, just 18 kV above the threshold. Yeah, as far as I know, this energy is the lowest 2 neutron energies above as a resonance. This is a very interesting case, I think.
25 is not bound.
25 is not bound, but the state is here, 750 kV. So oxygen 26 cannot decay through oxygen 25 energetically. It can decay only. So in this case, 2 neutrons actually emit democratically. Okay. So this is probably interesting for few body people, I think. I'm sure. Yeah. So this is the case. Okay. So it's okay. So now about oxygen 28, we also looked at how it decays. So for instance, this is the lowest three body system, 2 neutrons plus oxygen 24. And if you look at this, we just compared. So this gray histogram is the experimental spectrum, and then the others are. So the red one is a sequential through oxygen 26 simulation, and the blue ones are 5-body phase space decay. And this actually pointed that it actually decays through oxygen 26 ground state. Also, we looked at the other neutrons, higher energy neutrons. We also found that it is consistent with sequential decay through oxygen 26 ground state. Okay. So about the doubling magicity, what we did is that we used the cross-section. So we started from fluorine 29. The initial state was fluorine 29. And we just remove proton from here, basically. D5 half proton removed. But the neutron configuration of fluorine-29, as I said, fluorine-29 is in the island inversion. So this means that DFP are basically mixed like this. And for the case of fluorine-29 ground state, we know that P3 half is kind of dominated, and it forms a halo, actually, these two neutrons. Okay, so this means that if we have a large overlap with fluorine-29, if oxygen-28 has a large overlap with fluorine-29, then it means that the 2H bar configuration persists in oxygen-28. So that means that oxygen-28 is not doubly magic. But on the other hand, if oxygen-28 is doubly magic, the configuration of neutrons are totally different between fluorine-29 and oxygen-28, so that the overlap becomes nearly zero. Okay, so this is a kind of concept which we used. And the result was we extracted this cross-section 1.36 millibarns, and we extracted the overlap spectroscopic factor, which was 0.48. And compared with the theories now, the shell model calculations, EDF3, large-scale shell model, which predicted C² S equals to 0.68. So this large-scale shell model actually predict oxygen-28 is not doubly magic. And if we consider the reduction factor, so in the case of quasar-free scattering, we expect some reduction of the spectroscopic factor. And if we include this, this is almost consistent with this value of 0.48. On the other hand, if we assume the closed shell configuration and calculate it in the shell model, then we got C² S 0.13. So with this comparison, we concluded that n equal 20 neutron magicity disappears in oxygen-28. Okay. So this was shown by Francesca already. This is a comparison with theories for oxygen-25, 26, 27, 28. This is a ground state energy relative to oxygen-24. Okay. So this is 27 oxygen, 28 oxygen, and the theories. So this will give us some benchmark of theories, actually. So the theories can be categorized into conventional shell model, USDB, large-scale shell model, and ab initio calculations. We hear about the couple cluster method today, yes. And then also shell model with continuum effects, which is here, for instance. And actually, no theories are very well consistent with our results, but at least we found that 3 nucleon force is required to get better results. I think the one is, for instance, compared with conventional shell model, large-scale shell model, which includes 3 nucleon force, provides better better description, and also even with ab initio calculation, 3 nucleon force is important. And also the continuum effect seems to be playing important roles because it gives rather good agreement, although still there are some uncertainty. Okay, that's about oxygen-28. Okay, and still I have some time, right? So perspectives for the rest of the time. So I already discussed this neutron droplets. We would like to move on. Now we are here, tetraneutron, but still controversial. So we need to measure more, hexaneutron, and so on and so forth. So what I'd like to say is that so far, to measure these 4 neutron systems, basically people used, or we used missing mass. So missing mass is like, for instance, in this case of samurai experiment, helium-8 impinges on proton target, and the proton helium-4 is knocked out, like this. So what we measured is these momentum vectors, helium-8, helium-4, and protons. And from that, using momentum conservation, energy conservation, one can extract the mass of these 4 neutron systems, right? So this is called missing mass. The advantage of this method is that we don't need to measure neutrons. So you know that now that it's very difficult to measure multiple neutrons, right? So in this case, we don't need it. But on the other hand, the energy resolution is not so nice, usually 1 MeV at best. And we don't know the decay mode because we don't measure neutrons, so we don't know how neutron systems decay. Okay? So we would like to move to invert mass spectroscopy. Namely, we would like to measure directly these 4 neutrons, momentum, like what we did for Oxygen 28. So we have already started measuring 4 neutrons. And then using this simple formula, we can extract. We have good mass resolution of the order of 100 keV now. And the decay mode can be observed also. Like maybe we can distinguish 4 neutron democratic decay or 2 neutron or something like this, like we did for Oxygen 28. But we need to measure neutrons. Yeah, so this is a kind of headache. But we have some algorithm now, yeah. Indeed, by the current setup, this nebula, and now it is upgraded to Nebula Plus, which is basically equivalent to Nebula and Neuland combined in the case of Oxygen 28. So, and also we have another detector called Hime, which was also developed by our group originally, but now German group also joined. So we have lots of neutron detectors, basically made of plastic scintillators. So with that, we actually made a proposal. Meita Duo and Miki-san, these 2 people are PI of this experiment, and invariant mass for tetraneutron will be measured. This was approved experiment, okay? Okay, so this is one thing. But now, I'm a little bit more ambitious. I would like to measure more neutrons. So now we are actually developing new detectors. It's called NEODIS, Next Generation Neutron Detector Array. Okay, acronym I didn't show here, but anyway, NEODIS is called. Okay, so the problem is that, as I said, protons are recoiled, but the neutrons are scattered like this, okay? Like this. So well, even from the PhD, when I was a PhD, I thought that maybe we would like, how can we track neutrons? Neutrons that cannot be seen, right? Neutrons like a ghost for us. But if we know the track of protons, maybe we can conjecture the track of neutrons like this. Basically, this is like elastic scattering. So that was a kind of idea. So we actually proposed this project. So namely that these parts are plastic scintillators, and then these parts are plastic scintillators, but in between, we sandwich drift chambers. Drift chambers are tracking detectors. Very high quality tracking detectors. We can track protons like maybe 300 microns, 0.3 millimeter resolutions like this. Okay, so by doing that, we would like to measure multineutrons. Okay, this was I proposed this, and I got actually a grant for 5 years from 2024 to 2028. Okay, now so we are now developing this thing. Okay, so this is just already I mentioned. Okay, so now this is the original a plastic scintillator idea, right? We measure this, but basically we don't know where protons are emitted. Also neutrons are emitted, going. So it's rather difficult to distinguish between one neutron events and two neutron events like this. But once we have a tracking detector in between, then we know how neutrons are going. That's the idea. And the simulation tells us a nice spectrum like this. Even for hexagon neutron, we expect this kind of nice peak. This is not experiment, but this is simulation. But hopefully in 5 years, we would like to show you this kind of spectrum resolutions like this. Okay, with that, I'd like to summarize. It's maybe a little bit earlier, but key question is if there are any nuclei made of only neutrons. Okay, that's a very important question, I think. And I showed you the current studies about tetraneutrons. Okay, and I also showed multi-neutron cluster inside a nucleus. We may have 4-neutron systems like oxygen 24. So we observed oxygen 27, 28, as I showed you, published Nature. And perspectives are shown. So now we are moving from missing mass spectroscopy to invert mass spectroscopy for 4-neutron systems, 6-neutron systems. And we are now developing next generation neutron detectors called RA Neolis. Okay? With that, I'd like to finish, but I'd like to thank our collaborators. This is this tetraneutron measurement collaboration. And also, this is a collaboration for oxygen 2728. We had 88 participants from all over the world and from 25 institutes. Okay, with that, I'd like to thank you for your attention. Yes, questions?
Yes, and then there will be the discussion also with you and maybe with the others.
Yes.
It's the last time.
Yes.
Questions?
Any questions?
So if not, can I ask? Yeah. So in the oxygen case, it's quite interesting. And so before doing the oxygen isotope, so now you are thinking this is something and so double. How's the magic number? Then they should be stable. However, and after you perform the experiment, now in the oral state of resonance state, not so stable. So why so physically? So do you know the reason why? So that this is not so the stable, just as a resonance state.
Yeah, that's actually a question to maybe theoretician. So the theoretician says that it is related to three nuclear force. That is one thing. Yeah, so maybe you can have a look at this. I don't know where was it. Yeah, maybe Francesca has a comment. Why oxygen isotopes are unstable above oxygen 24?
Yeah, because this is also in the case of Sherman, it's a kind of magic number, double
I think
magic number,
this.
right? But so therefore that should be so stable. However, as a result, we know that just so in resonance state, it's something is unstable. So I want to see
from the perspective of the naive shot, one would expect that you mentioned
That's right.
However, as also was pointed out, we are here very close to the island of inversion, and so like potentially you can have different magic numbers when going towards the neutron drip line.
Right.
What we see from ab initio calculations is that actually, like when we have the three-body force, the oxygen drip line is at oxygen 24, and this is in agreement with also
But this
what
three
is seen
nuclear
at the
force was
experiment.
very important according to these
Yes.
people, right?
Yes, yes.
Nico, just talk please in the microphone. I cannot hear you.
So the due to the some so what mean slippery force make a repulsion or the,
Yeah,
what
I
is
think,
also the
yeah, I think it's repulsive.
repulsive?
No, because I think like probably the binding is going down, but it's going up in the last part. Like I have to look at the figure, I don't remember it very well. But due to the three body force, you see that's going up after oxygen 24. So you have that oxygen 26 is a bit above with respect to oxygen 24, and oxygen 28 is higher.
So that means if we use as a two-body force, then then three-body force is up, like this.
Yeah, so basically, like the three body force is creating a kink. So with respect to oxygen 24, the nuclei that come next are unbound. So they're not bound with respect to oxygen 24.
Maybe we can say that maybe oxygen 24 is so well bound. Is it another way? Because if
Yeah.
oxygen 24 is more bound than expected,
It's more bound than the ones.
then these guys become unstable, right?
Yeah, right. So then so we have just ask Francesco. Now, if I understand correct, then if we use only two-body force, then so the oxygen 28 is not a half bound state.
Yeah.
However, due to two-body force and repulsion, maybe the spin factor, then just up. Then finally, as a result, we don't have any bounds.
Right. Right. yeah.
Yes.
Am I correct?
Yeah.
But I'm not sure why. Because three-body force is just up. I want to see. Maybe next week, Otsuka-san will come. So therefore, I should ask.
So as I said, oxygen 24 is doubly magic now. Yeah. So that means that oxygen 24 is relatively stable, right? Comparatively stable, and then it goes down, and then this means that the others become comparatively unstable. Okay.
So that is so I want to know about this mechanism. Just I understand now is due to the three-body force repulsion. Then so this oxygen 28 becomes so the resonance state. But why so the three-body force becomes so repulsive? Also, I'm not sure. I don't know. Because in the three-body force sometimes is just always attractive and become
Yeah,
bound.
yeah.
But in this case, is just a behavior is just so an opposite side.
Right.
Then that is I don't know.
I see. Okay. Good question.
I just want to ask the following. Oxygen 25 is a D-wave resonance
Yes.
over oxygen 24.
Yes.
I was wondering about now oxygen 26, that is also a resonance.
Yes.
When the decay of oxygen 26, you see a neutron in D-wave. Can you identify that or not? Because oxygen 26 is 0 plus. So oxygen 25 is a D-wave resonance, as far as I remember.
Yeah.
So
there is a
can you
there is a
identify
discussion. Yeah, there is a discussion. Yes, about oxygen 26. Of course, D3 half. The resonance is due to D3 half. D3 half. But because we have now two neutrons, like D3 half, right? But since we have two neutrons, this can be mixed with other things like S1 half. And according to, I think, this Russian guy, what is his name? But anyway, even with a very small amount of S, can actually be effective to this decay, so that the width becomes okay. So if this is not existing, the lifetime becomes very long.
you need an S wave
Yeah.
in oxygen
26.
So the neutrons are in a mixture between D3 half and some way.
Yeah, the lower L is necessary, but even with very small amount, I think even less than 1% or something, this will affect the lifetime, because there was a very interesting experiment at MSU about oxygen-26 lifetime. Since the energy is very low, maybe it may show a very long lifetime, right? If it is like this. But yeah, so far the lifetime, well, the first experiment they show 3 picosecond or something, but the later looks like it's not so long. Maybe upper limit is like picosecond. Maybe someone here knows better, but I don't. But anyway, shorter lifetime, and this is due to the small mixture of this. Yeah, that is hard.
So probably if you look also to the angular distribution, not only the total energy of the, for example, of the 3 neutrons that comes from oxygen 25 populating 24, maybe you can also see, I mean, all this, if there is D waves or more S waves.
Okay,
because
so
I understand that it's very inclusive what you have done. I mean, those little
well,
peaks.
no,
So
this is basically exclusive measurement, but the so this one, for instance, 2 neutron incoincidence. This is invariant mass spectrum.
Yeah.
Okay, so basically we measured, but to extract the neutron angular correlation, we need a better, even better resolution. Okay, so this is because that, for instance, this is 18 kV, right? I think yeah, okay, so 18 kV. Okay, so actually I explained to one student once. So the relative energy is approximated like V1 minus V2 squared. And V1 is here, V2 is here. So the 2 neutrons, if you imagine 2 neutrons are like this, okay? And the relative, this is between 2 neutrons, but of course you have the third one, but whatever. But the point is that 18 kV means that, you know, this distance should be very small. This meaning that opening angle is also very small. Okay, so the neutrons are coming almost in the same direction, right? So, and then the angular correlation means that if you look at these 2 neutrons in the center of mass of oxygen-26, for instance, okay, so you know, you should measure these angles very precisely to extract the opening angle in the rest frame. So, so that actually these new neutron detectors, for instance, we showed, Neolith, can measure easily this kind of thing. Because with using Neolith, the position resolution becomes like millimeter level. The current neutron detectors like Nebula, this resolution is like, I say, 2 to 5 centimeter. You see? So, and for instance, if you measure this 18 kV state in in the current setup, which is like 10 meters from the reaction point, and this distance is like only 10 centimeter or something. Okay, so if you use a detector like 12 centimeter strip, then we cannot distinguish this anyway. So, but now we are moving to this millimeter range, so then we can measure this.
That's
yeah,
nice.
and also we need calcium-48.
Yeah. But you could also measure maybe the distribution of the relative angle between the oxygen-24 and the center of mass of the
That's
two
right, that's right,
neutrons
that's right.
as
Yeah.
well. But this maybe is just 0 plus, I don't know.
Yeah.
Just zero angular
I
momentum.
see.
Maybe
You
it's
think that this oxygen-24 neutron angle can provide us some information?
Information on the angular momentum.
Do you think so?
Yeah.
Okay.
I think.
Okay.
So-
Maybe then it's interesting.
More questions? Remember that soon we are going to ask again Takashi.
So you're preparing for the discussion session?
So then,
Yeah, maybe
have
we
the
can
break.
stop now, have the break, and come back with you.
Okay.
you can recover.
Okay.
Okay, so
Thank you.
thank you. So we are back at 4.
Okay.
No?
4.
40 minutes. Okay, so 10 to
10 to 4.
5.
10 to 4
10
is
to 4.
right.
Okay.
Thank you. Okay.
Really. No, I mean, this possibility to have, I mean,